The matrix method for unique solutions, non-singular case. Welcome, everyone. Before we dive into today's new topic, let's quickly recap where we left off. In our previous lesson, we explored how to take a standard system of linear equations and organize them into a much cleaner, more compact matrix form, which we represent as a times x equals b. Now, moving forward into this subsection, we are going to take that one step further. Instead of just representing the equations, we are going to learn the specific method to actually solve for those unknown variables tucked away inside matrix X. However, there is a specific condition we need to meet for this method to work. We will be focusing specifically on the case where the coefficient matrix, A, is what we call non-singular. We will define exactly what that means in just a moment. Understanding the non-singular case. First, we need to understand a key term, non-singular. We say a square matrix A is non-singular if its determinant, which we write as the absolute value of A, is not equal to 0. Why does this matter? Well, the importance of a non-singular matrix lies in the fact that a matrix has an inverse, denoted as a inverse, if and only if it is non-singular. In other words, the existence of that inverse depends entirely on this condition. On the flip side, if the determinant of A equals 0, we call the matrix singular. In this case, the inverse simply does not exist, which means we won't be able to use the algebraic derivation I'm about to show you in the next slide. Ultimately, for our system of equations to have one, and only one, unique solution, the coefficient matrix A must be non-singular. Keep this in mind, because as we move forward, checking if the determinant is non-zero will be your very first step in solving any problem. Now that we've established how to represent our system of equations in the matrix form, A times x equals b, let's dive into what makes this method work. Algebraic derivation of the solution. We begin with the matrix equation we established in the previous slide. A times x equals b. Our goal here is to isolate the variable matrix, x, so that we can find its individual values. To do this, we are going to multiply both sides of the equation by the inverse of A, which we denote as A inverse. However, there is a very important rule to remember here. You must multiply from the left side. Unlike regular numbers, matrix multiplication is not commutative, meaning the order in which you multiply matters immensely. If you multiply from the right, you won't get the correct result. Let's walk through the step-by-step derivation together to see how this works. First, we multiply both sides by A inverse, which gives us A inverse times the quantity A times x equals A inverse times b. Next, we apply the associative property of matrix multiplication. This allows us to regroup the matrices, so we can look at the quantity A inverse times A, all multiplied by x, equals A inverse times b. Now, remember from our definition of an inverse that A inverse times A results in the identity matrix, which we call ISO. Our equation simplifies to I times x equals A inverse times b. Finally, since multiplying any matrix by the identity matrix leaves it unchanged, we are left with our final, beautiful formula. X equals A inverse times b. So, to summarize this derivation, the unique solution for our variables is found simply by calculating the product of the inverse of our coefficient matrix and our constant matrix. This formula is exactly what we will be applying in the step-by-step procedure in the next slide. Now that we understand what a non-singular matrix is, let's look at how we actually use it to solve our equations. This is the algebraic derivation of our solution. Step-by-step procedure to solve the system. Now that we understand the theory behind why the inverse matrix allows us to isolate our variables, let's break this down into a clear, step-by-step procedure. If you follow these 5 manageable steps, you'll be able to solve any non-singular system systematically. Step 1. Your first task is to translate the algebraic equations into matrix form. You need to identify your coefficient matrix, which we call A, your variable matrix, which is x, and your constant matrix, which is b, so that you can write the equation as A times x equals b. Step 2. Next, you must calculate the determinant of matrix A. We denote this as the determinant of A. This is a crucial checkpoint. If the determinant of A is not equal to 0, you have a non-singular matrix, and you can proceed. However, if the determinant of A equals 0, stop right there. It means the matrix is singular, and this specific method for finding a unique solution cannot be applied. Step 3. Once you've confirmed a unique solution exists, you need to find the adjoint of A, written as A. To do this, you'll first find the matrix of cofactors for A, and then, very importantly, you must take the transpose of that cofactor matrix. Step 4. Now, we calculate the inverse of A. We denote this as A inverse. You'll use the formula where A inverse equals 1 over the determinant of A, multiplied by the adjoint of A. Finally, step 5. The last step is to compute the variable matrix X. You do this by multiplying the inverse of A by the constant matrix B. In other words, X equals A inverse times B. The resulting column matrix will give you the precise values for each of your unknown variables. In the next slide, we are going to put all these steps into practice with a real-world nutritional example to see how this works in action. Real-world example. Imagine a nutritionist is preparing 3 different health mixes using 3 ingredients: almonds, walnuts, and cashews. We are given the total weight of each mix and the cost per kilogram, and our goal is to find the cost per kilogram of each individual ingredient. We can represent this problem using a system of linear equations. Let x, y, and z represent the costs per kilogram for almonds, walnuts, and cashews, respectively. Our equations are x plus y plus z equals 10, 2x plus 3y plus z equals 18, and x plus 2y plus 3z equals 22. To solve this using the method we just derived, we follow a 5-step procedure. Step 1. We must first write the system in matrix form. X equals B here. Matrix A is our coefficient matrix, containing 1, 1, 1 in the first row, 2, 3, 1 in the second row, and 1, 2, 3 in the third row. Matrix X is our column of unknowns, X, Y, and Z. Finally, matrix B is our constant matrix, containing 10, 18, and 22. Step 2. Next, we calculate the determinant of A to ensure a unique solution exists. Expanding along the first row, we get 1 times the quantity 3 times 3 minus 1 times 2, minus 1 times the quantity 2 times 3 minus 1 times 1, plus 1 times the quantity 2 times 2 minus 3 times 1. This simplifies to 1 times the quantity 7, minus 1 times the quantity 5, plus 1 times the quantity 1. This gives us 7 minus 5 plus 1, which equals 3. Since the determinant is 3, which is not 0, the matrix is non-singular, and we can proceed. Step 3. Now, we find the adjoint of A. This requires us to find the cofactor for every element. For the first row, the cofactors are 7, -5, and 1. For the second row, they are -1, 2, and -1. For the third row, they are -2, 1, and 1. We arrange these into a cofactor matrix, and then take its transpose to find the adjoint of A. The resulting adjoint matrix has 7, -1, and -2 in the first row, -5, 2, and 1 in the second, and 1, -1, and 1 in the third. Step 4. With the determinant and the adjoint, we can now calculate the inverse of A. We take 1/3 and multiply it by our adjoint matrix. Step 5. Finally, we solve for our variables by computing x equals the inverse of A multiplied by b. We multiply each row of our inverse matrix by the column matrix B. For the first row, we calculate 7 times 10 plus -1 times 18 plus -2 times 22, which results in 70 minus 18 minus 44, giving us 8. For the second row, we have -5 times 10 plus 2 times 18 plus 1 times 22, which is -50 plus 36 plus 22, resulting in 8. For the third row, we have 1 times 10 plus -1 times 18 plus 1 times 22, which is 10 minus 18 plus 22, resulting in 14. After multiplying by the 1/3 factor, our final solution for x is a column matrix containing 8/3, 8/3, and 14/3. These are the costs per kilogram for our 3 ingredients. Now that we have understood the theory behind the non-singular case, let's apply it to a practical, real-world scenario. As we move to the next slide, pay close attention because even a small error in these steps, like a sign error or forgetting to transpose, can lead to an incorrect result. Common mistakes to avoid. Now, before we wrap up our lesson and look at the final summary, I want to pause and discuss some common pitfalls. Even if you understand the theory, it is very easy to make small computational errors that can derail your entire solution. First, let's talk about the multiplication order. This is a very frequent mistake. When you are solving for x, you must calculate the inverse of a multiplied by b. Do not calculate b multiplied by the inverse of a. Remember what we discussed in the algebraic derivation on slide 3. Matrix multiplication is not commutative. You must multiply the inverse from the left side to ensure the equation remains valid. Second, keep a close eye on your signs when calculating cofactors. When you are building your cofactor matrix, you must follow the specific sign convention. It follows a checkerboard pattern, starting with plus in the first position, then minus, then plus, moving to the second row with minus, then plus, then minus, and finally the third row with plus, minus, and plus. Forgetting to flip that sign for the minus positions is a very common way to lose marks. Third, please do not forget the transpose step. As we saw in our nutrition example on the previous slide, the adjoint is not just the cofactor matrix. It is the transpose of the cofactor matrix. Many students do all the hard work of finding the cofactors, but then forget to switch the rows and columns. If you skip the transpose, your inverse will be incorrect. Finally, be extremely careful with your initial determinant calculation. As we learned, the determinant is the foundation of the entire process. If you make even a tiny arithmetic error while calculating the determinant of a, it will lead to an incorrect inverse, and your final values for the variables will be entirely wrong. Take your time with these steps, and you will find the process much more reliable. Key takeaways. First, remember that a system of linear equations will have one, and only one, unique solution, provided that our coefficient matrix, A, is non-singular. In mathematical terms, this simply means that the determinant of A, denoted as the absolute value of A, must not be equal to 0. If the determinant is 0, we cannot proceed with this specific method. Second, the core formula you need to memorize for finding your variables is x equals a inverse multiplied by b. This is the goal we are always working toward. Third, recall how we actually find that inverse. The formula for a inverse is 1 over the determinant of A, multiplied by the adjoint of A. This is where most of your computational work will happen. Finally, if you ever feel lost during a problem, just follow this logical flow. Start by calculating the determinant, then find your cofactors, move on to the adjoint by transposing those cofactors, use that to find the inverse, and finally, perform the matrix multiplication with matrix B to get your result. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of the matrix method. If you follow these steps carefully and avoid the common pitfalls we discussed, you'll be able to solve these systems with confidence. Great job today!